In this lecture, we're going to discuss exact differential equations and integrating factors and how to solve equations of this form. So first of all, let's define what is an exact differential equation. By the way, this can be found in section 1.4 of your textbook CRASIG. And then I've taken a significant portion of this lecture from an online source that I think explains things a little more clearly. So I'll refer to that throughout the lecture as well. So for a given differential equation, such as the one shown below, where we have some function of x and y times dx plus some function of x and y times dy equals 0, we can determine whether or not this function is exact by using the definition of exactness. If we take a general function u of x and y, and we basically take its derivative du, or its differential du, that's obviously equal to the partial derivative of u with respect to x times dx, plus the partial derivative of u with respect to y times dy. And so notice that this equation, which is the perfect differential of du, looks very similar to this equation if the following conditions are met. And that is, if the function m is equal to the partial of u with respect to x, and if the function n is equal to the partial of u with respect to y, and if du is equal to 0. So if these three cases are met, obviously if du is equal to 0, it's very easy to integrate u and get the constant c, and then that allows us to obtain a solution. This is referred to as an implicit solution, and that's in contrast to a solution where we would have y given as some function of x, which is called an explicit solution. So this defines whether or not a differential equation is exact. So we have basically a very simple test for exactness, and that is if we differentiate m with respect to y and we differentiate n with respect to x, because of what m and n are equal to, basically this means that both of these derivatives will be equal to the partial of u with respect to y and with respect to x. So because these two terms are equal, then what that tells us is the partial of the function m with respect to y must equal the partial of the function n with respect to x. And if that is true, then the differential equation is an exact differential equation. So once again, this bottom equation here is the test for exactness on a given differential equation. So the algorithm to solve exact differential equations is as follows. So the first thing we do is we identify the function m, and we integrate that with respect to x, ignoring the constant of integration and treating all of the y terms in the equation as constants because we're specifically integrating with respect to x. We then identify the function n, and we're going to integrate that with respect to y, once again ignoring the constant of integration and treating all of the x's in the equation as constants because we're only concerned with integration with respect to y. If we now take all of the factors that come out of the first integration and all of the factors that come out of the second integration, and we combine those and sum them together, then that basically forms a general solution to the differential equation. We set that general solution equal to a constant, and that forms our family of solutions. So the next slide is going to illustrate an example of this, and once again, I've used the website given above in order to pull this example because I think it's a very clearly defined and written example. So here's our problem. This equation right here is our differential equation that we would like to solve. Let me get a pen here. So we'd like to solve this equation. And so the first thing we do is we identify the function m, which is going to be this first part. And we're going to take that and integrate it with respect to x and ignore the arbitrary constant of integration. So here's that function m plugged into an integral, and when we integrate that, we get the following: xy squared minus x squared. And notice that we've done an indefinite integral, but we've temporarily neglected to incorporate the constant. Now we want to identify the factor n. That would be the second term. So if we now take n and we integrate it with respect to y, then we get the following, xy squared plus y. Now notice that the xy squared term is included in both solutions. We're only going to count it once. Notice that we have a term minus x squared, and we have a term y. So what we want to do is we basically take all three terms, our xy squared term, our xy squared term, our minus x squared term, and our plus y. We sum those together. So notice the key is this xy squared term, even though it appears in both solutions, it's only incorporated once into our solution. So we take the sum of those three and we set it equal to a constant. Now sometimes equations aren't exact as they're written, and so we can actually make them exact by using something called an integrating factor. So this is the definition or theorem that comes from your textbook, where we have a non-exact equation, where we have some function p and some function q, and clearly this would not meet the definition of exactness. And so we could make that exact by multiplying by some unknown function f, and that function is called an integrating factor. So the next set of slides will be to discuss how to determine or how to find an integrating factor. The notation is going to be a little bit different because once again we're switching back to this website, this web-based source, in order to get a little more clean example. So how to find an integrating factor. So here is our differential equation, and we're just going to make the assumption that this differential equation is not exact. So we're going to define a function mu of x and y and say that if we take mu of x and y and we multiply both sides of our differential equation by mu, we can make that exact. And so this function mu is called an integrating factor of the original equation. And it's guaranteed to exist if the differential equation actually has a solution. So integrating factors will turn non-exact equations into exact ones. And so now we want to look at how would we find an integrating factor, and it's basically an algorithm that's outlined here. So the first case, let's take our differential equation m dx plus n dy is equal to 0. Say that it's not exact, meaning that the derivative of m with respect to y will not equal the derivative of n with respect to x. And by the way, in this particular set of notes, this little n with a subscript x, that's referring to the derivative of n with respect to x. This is referring to the derivative of m with respect to y. So it's just a different kind of notation. So what we look at is we look at the derivative of m with respect to y minus the derivative of n with respect to x divided by the function of n. And what the theorem says is if that is a function of x only, then we're going to call that function epsilon of x. And our integrating factor can be determined by taking e, the exponent, to the power of the integral of epsilon of x dx. So that's going to be our integrating factor mu. Case 2 is quite similar. Case 2 operates off of a slightly different test equation. So we take the derivative of m with respect to y and we subtract the derivative of n with respect to x, and we divide by minus m. If that is a function of y only, then we're going to denote it by psi of y. And then our integrating factor can be found by taking the exponential to the integral of psi of y dy. And that will give us an integrating factor of our given differential equation. So there are two possibilities. One, that we get a function of x only, and another that we get a function of y only. So to solve an exact equations, the first thing obviously that you do is you check for exactness. If it's exact, then you solve as we did in the previous example. If it's not exact, then what we want to do is check for an integrating factor, case 1. If we don't meet the criteria for case 1, then we want to check for an integrating factor, case 2. Once the integrating factor is determined, we can multiply that ordinary differential equation by the integrating factor and proceed as previously determined. So let's look at an example. Here's a differential equation. And so the first thing we want to do is we want to test for exactness. So we take the derivative of m with respect to y, which is done here, and yields the following result. Sorry, let me go back and get the pen. So that's going to yield the following result. And then what we do is we take the derivative of n with respect to x, the partial, and that's going to yield this result. Now remember, for the equation to be exact, these two terms must be equal. So because they're not equal, it means our equation is not exact. So the first thing we want to do is we want to try a case 1 test. So we take our derivative of m with respect to y and our derivative of n with respect to x divided by the function n. So that's done here in this step. And after doing some algebra, we find that that is equal to 1 over x. So that basically means that this is a function of x alone, and it satisfies case 1. So now we're going to use the criteria for case 1 to find our integrating factor. So this little equation right here is where we're actually finding mu of x, our integrating factor. So we take the exponent, raise it to the power of the integral of this function, 1 over x dx. That's going to be the natural log, and then e to the natural log of x is actually x. So our integrating factor is x. So that's repeated here. Our integrating factor is x. So now what we do is we take our original equation and we multiply it, and we replace m with mu times m. So basically that means our original m is now multiplied by x, shown here in this first term. And this set of notes is referring to that as m bar. And then we take our n term and we multiply it by x, referring to that as n bar. Okay, and now if we run the exactness test on m bar and n bar, we find that the derivative of m bar with respect to y is indeed equal to the derivative of n bar with respect to x. So this new function does meet the criteria for exactness. So we're going to solve this exactly the way we did in the previous section, where we're going to take m bar in this case, and integrate it with respect to x, treating y as a constant and ignoring the constant of integration. So when we do that, it's very annoying to have to get this pen every time. So when we do that, we get the following expression. And then when we integrate n bar with respect to y, we get the following expression. And notice that they're exactly the same. So what that means is that I don't either one of these functions would suffice as a general solution. So I take each factor and I represent it once to get my general solution, setting that equal to a constant c. So that really concludes the methodology of how to use integrating factors, or the discussion of the methodology of how to use integrating factors to solve exact differential equations and how to solve exact differential equations. Now, as oftentimes, and we have not really discussed initial value problems yet, but oftentimes you will be given an initial value or a boundary condition that allows you to determine this constant. If this constant is determined, then you can get a single curve in x and y. If the constant is not determined, then what you have is basically a family of curves or a family of solutions. So that allows you then to generate the solution of these differential equations. And a lot of times the solution will need to be graphical because some of these are actually very hard to visualize.